Okay, so this time around we're going to take a look at differentiation and integration of vector-valued functions. Now that we're familiar with what such functions are and how to graph their curves in the plane and in space. So we'll move on and talk about how to differentiate the vector-valued functions and integrate such functions. So we'll start with the derivative of a vector-valued function. So say you have a vector-valued function r. If you want r prime, you just do the limit as the change in t approaches 0 of that function evaluated at t plus delta t minus the function evaluated at t all divided by delta t. So it just mimics the limit definition of a traditional function in x and y. Of course, the limit needs to exist for the derivative to exist. So no surprises here. It's basically the exact same definition that we're used to in single variable calculus. Alright, so that's the limit definition. Well, what about our shortcut formulas? Are we going to have to learn a bunch of new shortcut formulas? Well, let's see. Let's say you have a vector-valued function with two components, f of t component functions, f of t and g of t. So this would be in 2 dimensions. So we could extend this idea to 3 dimensions if we needed to. So using the limit definition, r prime would be the limit as the change in t approaches 0, and then we evaluate r at t plus delta t. So that'd be f of t plus delta t times vector I plus g evaluated at t plus delta t times vector j minus the function itself, all divided by delta t. Well, if you distribute this negative, use the commutative property, we can rearrange it to where we have f evaluated at t plus delta t minus f of t all over delta t, plus we can put the g evaluated at t plus delta t with the g of t all divided by delta t. And using our limit laws, we can do the limit of this expression plus the limit of this expression. Well, the limit of this expression, that's simply f prime. That's just f prime. So you have f at t plus delta t minus f of t all over delta t. That's just f prime of t. You can factor the vector I out. And then this is just g prime. So you have g evaluated at t plus delta t minus g of t all over delta t. That's just g prime. So basically, r prime is just going to be the derivative of f plus the derivative of g. So you just do the derivative of each component function to get the derivative of r. So, in 2 dimensions, if your vector-valued function is defined using f of t for the first component function and g of t, then if you want the derivative of that vector-valued function, it would just be f prime plus g prime, along with, of course, the standard unit vectors I and j. In 3 dimensions, no surprise, you're just going to have that third component function h, so it would be h prime when you go to do the derivative. So that makes finding the derivative a fairly straightforward process. So let's take a look at one. So let's say we've got r of t is equal to t times vector I plus t squared plus 2 times vector j, and we want the derivative. So r prime, well, the derivative of t is 1, so we would just have 1 times vector I. The derivative of t squared plus 2 is just 2t. So there's r prime. And then it says sketch the given function, the function evaluated at 1, and the derivative at 1. Well, the derivative at 1 would just be I plus 2j, and just the original function evaluated at 1 would be I plus 3j. So if we go to sketch this, Let's see what we get. Well, let's say we plug in t equals 0. You'd have 2j. So 2j would terminate there. Say we plugged in 1, we'd have 1, 3. So that would terminate there. So we plug in 2, we'd have 2, 2 squared 4, 2, 6. Say we plugged in -1 for t, we'd have -1, 3. Say we plugged in -2, we'd have -2, 6. Oh, whoops. This wasn't a -2, 6. So basically we're looking at this curve here with this orientation. So that would be R. Well, R evaluated at 1 was 1, 2. So that was this point. So that's this one here. Oh, wait a minute. So actually that was the derivative evaluated at 1. Derivative evaluated at 1. So R of 1 was 1, 3, so 1, 3 was this. So when you go to plot R prime at 1, the derivative evaluated at 1, the way this works is you go to, when t is 1 on the original vector valued function, that vector terminates at 1, 3. So that's where you're going to start. That's going to be the initial point of the derivative function's vector when t is 1. So from there, so starting here, it's 1, 2. So you go right 1, and you go up 2, 1, 2. So that's the derivative evaluated at 1 is that vector there. So the derivative function evaluated at 1, that's going to uses the terminal point of R1 as its initial point. Alright, so let's try another one. Let's see. So we've got this vector valued function, cosine of t times vector I plus sine of t times vector j plus 2t times vector k. So now we're in space, three-dimensional situation here. So let's find the following. Let's do the derivative. Well, the derivative of cosine with respect to t is going to be negative sine t. Derivative of sine with respect to t, that'd be cosine. Derivative of 2t would be 2. If we want the second derivative, that would just be the derivative of the first derivative. So derivative of negative sine t would be negative cosine t. Derivative of cosine t, let's see, it'd be negative sine t. Derivative of 2 would be 0, so we'd have 0 times that vector. Well, 0 times that vector just is 0, so we don't need that. what if we do the dot product of the first derivative and the second derivative? So let's see what we end up with there. That would be sine t cosine t. So you multiply their first components and then add the product of their second components, which would be, and then you add the product of their third components. So we end up with 0. What if we do the cross product of the first derivative and second derivative? Let's see. That would be do cosine t times 0 minus 2 times negative sine t times I minus negative sine t times 0, 2 times negative sine t. No, I think I grabbed the wrong one there. That would be cosine t j, and then plus negative sine t times negative sine t. Then minus cosine t times negative cosine t. Fit this in there one way or the other. Okay. And then we can clean that up. That'd be 2 sine t times vector I minus 2 cosine t times vector j plus k. So that would be their cross product. So that, again, that would be the result. You know, when you do the cross product, you're talking about a vector that's orthogonal to the two given vectors. So for any value of t, this output's going to be orthogonal to the first derivative and second derivative. Evaluate that same value of t, those two vectors. All right, so a given vector-valued function r is considered smooth on an open interval if the derivative of the first component function, derivative of the second component function, and the derivative of the third component function are continuous on that interval, and the derivative never equals 0 for any t on that interval. So for a vector-valued function to be smooth, we need the derivatives of the component functions to all be continuous on the interval, and the derivative of the vector-valued function to never be 0 for any t in that interval. All right, so with that in mind, let's find all intervals on which the curve represented by this vector-valued function from 0 to 2 pi is smooth. So let's see if we can figure out where this thing is smooth. Well, let's find the derivative. So the derivative of this vector-valued function, well, that would be negative 5 sine t plus 5 sine 5t times I plus 5 cosine t minus 5 cosine 5t j. Well, this is f prime, and that's continuous for all t, because sine is a continuous function, sine of 5t is a continuous function, and the sum of two continuous functions is continuous. And then this is g prime, and it's continuous for all t. For the same reason, because cosine and cosine of 5t are both continuous functions, and their sum or difference is also continuous. Okay, so we've met that condition that our derivatives for the component functions are continuous on some interval. And they're definitely continuous from 0 to pi, because they're actually continuous for all values of t. But now we need to see when would the derivative be 0. Well, the derivative would be 0 when f prime of t equals 0 and g prime of t equals 0. Because if this was 0 and this was 0, then we'd have 0 times this would be 0, times this would be 0, so the whole thing would come out to be 0. Well, let's see when that would happen. So when does negative 5 sine t plus 5 sine 5t equal 0? So in other words, when does sine of 5 times a number minus sine of that number come out to be 0? Well, let's see. So if t was 0, sine of 0, you get 0 minus, so if 0 worked. So basically, when does sine of 5t come out to be the same thing as sine of t? Because if they're the same, when you subtract them, you'll get 0. And that's going to happen at 2 pi also, because you'd have sine of 10 pi and sine of 2 pi. Well, that's both of those are 0. It would also happen at pi over 2, because sine of 5 pi over 2 and sine of pi over 2, let's see, those are both 1, so 1 minus 1 would be 0. Same thing for 3 pi over 2, and same thing for pi. And then the other one, 5 cosine t minus 5 cosine 5t, when would that be 0? So when is cosine of t minus cosine of 5t going to be 0? In other words, when are cosine of t and cosine of 5t the same value? Again, we're only considering 0 to 2 pi. And that's at 0, 2 pi, pi over 2, 3 pi over 2, and pi. So r prime is equal to 0 for, let's see, 0, 2 pi. I guess we go in numerical order. Pi over 2 showed up in both. Pi showed up in both. 3 pi over 2 showed up in both. And 2 pi. So the given vector valued function is smooth on the following intervals: 0 to pi over 2, open intervals, mind you. So it's not smooth at those t values, so those t values can't be included in any intervals for which this thing is smooth. Alright, so what are some properties of the derivative? Let's see, say you have vector r and vector u. Say they're both vector valued functions that are differentiable. Let w be a differentiable function of t, so not a vector valued function, just a traditional function, and let c be a scalar. So say you want the derivative with respect to t of a scalar times a vector valued function. Well, you would just do the derivative of the vector valued function, r prime, times the scalar. Exact same rule we're used to in single variable calculus. Say you want the derivative with respect to t of the sum or difference of two vector valued functions. Well, you would just do their derivatives individually and add or subtract them. Again, same exact property we're used to in single variable traditional function calculus. What if you want the derivative of a traditional function times a vector valued function? So it's basically ended up being the product rule that we're used to from the beginnings of calculus. So it'd be w of t times the derivative of the vector valued function plus the derivative of w times the vector valued function itself. What if you want the derivative with respect to t of the dot product of r and u? Well, then it would be r dot u prime plus r prime dot u. If you want the derivative with respect to t of the cross product, it would just be you would do the cross product of r and the derivative of u, and then add to that the cross product of r prime and u. And if you want the derivative with respect to t of the vector valued function r evaluated at the function w, you would just do r prime with w plugged in times w prime, so our chain rule that we're used to from the beginnings of calculus. And then one more. If a vector valued function dot itself is a constant, then that function dot its derivative will be 0. So these are all properties involving the derivative of a vector valued function. Again, presented without proof. We can discuss why these work at a later time, if need be. So let's say you have a vector valued function r defined with these 3 component functions and u defined with these 3 component functions. Let's say we want the derivative with respect to t of their dot product. Well, let's see. The derivative of r, 1 over t, its derivative would be negative 1 over t squared. Derivative of negative 1 would be 0, and the derivative of natural log t is 1 over t. The derivative of function u would be, let's see, 2t times function I minus 2 times function j. The derivative of that would be 0. Well, let's see. The derivative with respect to t of function r dot function u, using our property, that would be r dot u prime plus r prime dot u. So it's going to be 1 over t times 2t plus negative 1 times negative 2 plus natural log of t times 0 plus negative 1 over t squared times t squared plus 0 times negative 2t plus 1 over t times 1, which comes out to be 3 plus 1 over t. So the derivative with respect to t of the dot product of those 2 functions will be 3 plus 1 over t. But we also want the derivative with respect to t of the cross product of u and its derivative. Well, that property states that we should just do u cross the derivative of this one, which would be u double prime, plus u prime cross u prime. So we need the second derivative. So the second derivative of u is going to be 2i. Derivative of negative 2 is 0, so that would just be 0. Okay, so we've got u prime, u double prime, and we've got u. So we got everything we need. Let's see. So this is going to get kind of lengthy because we're doing a cross product. So this would be, let's see, negative 2t times 0 minus 1 times 0 I minus t squared times 0 minus 1 times 2j plus t squared times 0 negative 2t times 2 k plus, and then we still have to do the cross product of u prime and u prime. So we clean that up. That is 2j plus 4tk, because that just comes out to be 0. Plus, now we got to do this cross product. So it's going to be negative 2 times 0 minus 0, negative 2. And if we clean that up, that's 2j plus 4tk, because that'll be 0, that'll be 0, and that'll be negative 4t plus 4, that'll be 0. Okay, what about integration? Well, let's say you have R with two component functions f and g, and let's say they're continuous on an interval a to b. Then the antiderivative of the vector valued function r, you'll just do the antiderivative of function f, the antiderivative of function g, and that'll yield the components we need for the antiderivative of the vector valued function r. And if it was a definite integral, a Riemann sum, then if you want a to b of that vector valued function, you just do a to b of function f, a to b of function g, and those will be the components that we need for the definite integral a to b of the whole vector valued function itself. And then if it's got three components, you just extend it to include the third component. So you just do the antiderivative of h, or the Riemann sum of h from a to b. So again, no surprises there if you extend it to three component functions. So for example, say we want the antiderivative of the vector valued function t times vector I plus 3 times vector j with respect to t. Then we'll just do the antiderivative of t with respect to t, and the antiderivative of 3 with respect to t. So that's just going to be 1/2 t plus some constant plus 3t plus some constant. So then we'd have, that'd be t squared, forgot my squared. Raise the exponent by 1, so that'd be 1/2 t squared I plus 3tj plus c1I plus c2j. But this is just a constant vector, it doesn't depend on t. So we'd have 1/2 t squared times vector I plus 3t times vector j plus just some constant vector c. So say we have the derivative of some vector r and we want the antiderivative, and we know that the original function r evaluated at 0 is this particular vector. So it's basically doing a similar to a differential equation with an initial condition. So r, it's a pretty goofy looking r, I apologize, would just be the antiderivative of cosine 2t I minus 2 sine tj plus 1 over 1 plus t squared k with respect to t. Alright, so let's see what that would be. So the antiderivative of cosine 2t, that would be 1/2 sine 2t plus some constant. Antiderivative of negative 2 sine t plus some constant. And the antiderivative of 1 over 1 plus t squared would be inverse tangent plus some constant. Well, we know that the original function at 0 comes out to be oh wait, well, I guess before we use that, why don't we go ahead and plug in 0 for our vector valued function here. So sine of 0 is 0, so that would be c1i. And then cosine of 0 is 1, so that would be 2 plus that constant j. And then inverse tangent at 0 is 0, so that would be constant k. But we know that the original function evaluated at 0 is actually 3, negative 2, and 1. So this is supposed to equal 3i minus 2j plus k. In other words, c1 is 3, c2 is negative 4, and c3 is 1. So the original function must have been 1/2 sine 2t plus 3 vector I plus 2 cosine t minus 4 times vector j plus arctan t plus 1 times vector k. So this is the vector valued function that has that derivative and contains that vector. That terminal point would be on the curve of this vector valued function r.